Okay, great. So hello everyone and welcome to Shenanigans. Tonight my colleague Sheraz and I are going to introduce the topic of generative adversarial networks. This is a huge and fascinating topic that we knew nothing at all about when we started. So in the next 15 minutes, we're just basically going to scratch the surface with you. And we also really hope that you enjoy bad puns. So just to get everyone on the same page, what on earth is a GAN and why do we care? Well, in machine learning, we spend a lot of time looking at discriminative models like classifiers that look at a set of data and say, okay, given these features, I predict that it should be mapped to that class label. GANs are a type of neural network architecture that falls in the class of generative models, and they allow us to sort of do the opposite and say, okay, given this label, let's learn the distribution of that class and use that information to generate new data that fits that distribution and therefore belongs in that class. This ability is highly useful. We can use it to create more of data that may be sparse. We can enable machine learning to work with multimodal outputs, and we can do a lot of things, cool things in particular with images. So this pix-to-pix is a GAN example that allows us to easily see how given labels, the computer can fill in the features of the pictures, such as with labels to street scene or labels to facade. It can do this edges to photo operation. It can fill in or change the colors of pictures, a lot of really neat stuff. Another example is super resolution, in which we need to be generating more data to impute additional information into the image in order to make it sharper than it was before. So today we're going to go over how exactly GANs work, a few use cases and different types of them, and then we're going to show some example code that demonstrates how a simple GAN might be built in Python with TensorFlow. I'm going to talk fast because I got a lot to say. So to give a brief bit of history, generative adversarial networks are only about 4 years old. The first GAN paper came out in 2014. It was written by a guy named Ian Goodfellow, who is currently working at Google Brain. And the basic architecture that he published is that of a network with two members who are adversaries. The two members are generally described as a forger or a counterfeiter and a detective. And the concept is pretty simple. The forger's goal is to make something so realistic that the detective can't tell it's fake. And the detective's goal is to correctly identify real from fake. So in GAN architecture, the detective is called the discriminator and the forger is called the generator. And they're both neural networks that are pitted against each other in this zero-sum non-cooperative game. What happens is that the generator takes some noise vector and uses it to create fake data. And the discriminator looks at samples of real data and then is fed both real and fake data and starts to make predictions about, is the data that I'm seeing now real or fake? In other words, does the density distribution of this data match what I know about the density distribution of the real data? So then the discriminator outputs a probability value for whether or not a given piece of data is fake. Then, because both the real data and the fake data are labeled, this becomes a supervised learning problem. And the results of the prediction can backpropagate, update weights in the discriminator and the generator networks before the next round. So while at first the generator is putting out nonsense data, it's very easy for the discriminator to say that's obviously fake. But over time, if the balance is set properly, the generator learns the distribution of the real data and gets so good at mimicking it that we hit an equilibrium of 50% probability, meaning that the discriminator can't tell if the data is coming from the real set or the generator. So that's the point at which you're hopefully getting new good data that looks like it came from the original distribution. Here we can see a GIF of a GAN going through multiple iterations on the MNIST dataset and learning to generate images that could pass as handwritten numbers. Looking into how this works mathematically, in the original GAN, we are minimizing something called the Jensen-Shannon divergence, which is a method of measuring the similarity between two probability distributions. So we're essentially trying to minimize the distance between the distribution of the real data and the distribution of the generated data. And the objective function for a simple GAN does this with the log. We don't have to use a log. Different types of GANs use different cost functions, but for today we're just gonna look at the original. So As you can see in the equation, we are working with the data distributions of the noise as well as the original data set, which come from the samples. And then we have the parameters of the generator and the discriminator that are updated via backpropagation. So we can look at the left side of this equation as representing the discriminator's point of view. It represents the output on data from the real sample. So of course we want to maximize the probability of classifying real data as real. And we can look at the other side as representing the generator. And the generator wants to minimize the probability that the discriminator will classify its data as fake. So I hope that makes sense, but this is the framework for the minimax game that's being played in a GAN. Here is from an excerpt from the 2014 paper, the original GAN paper, where it's talking about with each iteration, we're updating the discriminator by ascending its stochastic gradient and updating the generator by descending its stochastic gradients. This concept is pretty intuitive actually, and hopefully makes sense, but in practice it can be pretty difficult to actually implement. At some point we need to get convergence between the discriminator and the generator in order to be getting good images. And sometimes when we're trying to do this, we run into a problem of non-convergence, where however we've set our hyperparameters or our cost functions, the gradient has resulted in something that will never converge. This is actually a really common problem and can make it really hard to train a GAN. Another thing that can happen is the discriminator getting too smart too fast and sort of cutting the generator off, and that can result in a diminished gradient. Or if the generator learns to focus on only some parts of the data distribution and not others, all of your fake data can start to look similar. If you look at the pictures that have the same color bars under them, you can see that they look kind of similar, and that's not what you want. You want a wide variety of stuff that your generator is producing. Finally, GANs tend to have really high hyperparameter sensitivity, and tweaking one thing a tiny bit can result in a lot of different outputs. Sheraz will talk a little bit about that when he goes through the code. Once you do train and optimize your GAN, however, there are many different things you can do. We talked about super resolution and image generation. People have used GANs to generate fake celebrity faces. They've used it to take an image of a person and kind of map it to a new target pose, which I think is most creepy. They've used that to generate music, 3D objects, video. There's a company in Baltimore using them to generate new candidate molecular structures for drug candidates. Last week, today, a painting made by a GAN sold for over $430,000 in New York. The real data that was used to make this portrait was over 15,000 portraits that were painted between the 14th and 20th centuries. If you look at the bottom corner, they actually put the equation for GANs into the portrait itself, which is pretty cool. And the last thing I'm going to talk about, but not go very deep into, is the fact that there are many, many different types of GANs that improve upon the original. One example is DC GANs, or deep convolutional GANs, which use a convolutional neural network, which Dave was just talking about. Instead of a multi-layer perceptron as a generator, it gets much better image results. Another type is the Wasserstein GAN, which uses a different cost function to minimize the Earth mover distance, or Wasserstein distance, instead of the Jensen-Shannon divergence. What this does is make it a lot easier to see when you've hit a point of diminishing returns with your training, and it also corresponds to image quality, which is nice. And there are also conditional GANs, which allow us to kind of control what our GAN is generating with text strings. And there are many, many more types of GANs, some of which will be covered in the next presentation, that do a lot of different things for a lot of different purposes. After this, I'm going to switch over to Sheraz, who's going to show you what a GAN actually looks like in Python with TensorFlow.
Thank you, Emily. I'm going to talk about coding a GAN with TensorFlow. So at first, we wanted to use the MNIST dataset to generate images of handwritten digits. Unfortunately, we realized that training this GAN takes close to a day without a powerful GPU. So we settled for crawling. We're going to generate a simple parabola with 200 sample data points. Fortunately, 10,000 iterations of this GAN run in 5 minutes on my machine. GANs can be very expensive computationally. The next problem I ran into was TensorFlow and Anaconda not behaving. Anaconda would not recognize TensorFlow. I, through multiple searches, found that these steps allowed me to use TensorFlow with Anaconda. I had to create a separate environment for TensorFlow. So tweaking the model, we're using a parabola with 200 data points as our real data. The generator and discriminator learning rates are very important because as Emily talked about, we don't want the generator or the discriminator to overpower the other. We can also tweak the generator steps and the discriminator steps. The number of iterations is also very important because we want to run the model long enough that it reaches an equilibrium. Different models will reach an equilibrium at different levels of iteration. We ran 10,000 iterations for our GAN. We also tried 2 different optimizers. The Atom optimizer is very popular with GANs, but we actually found that the RMS prop optimizer worked better for us. Here are the adversaries. The generator is a neural network with 2 hidden layers, and the discriminator is a neural network with 3 hidden layers. The placeholders, logits, and optimizers. So first we create placeholders in TensorFlow. We then define the map probabilities for the real data and the generated data. We pass this to a loss function, and then we optimize the loss function. And as I stated earlier, we're using the RMS prop optimizer. Let's train. So GANs are all about iterations and gradual improvement. A GAN literally takes noise and generates something wonderful out of it. As you can tell here, we have a for loop that's going to run for the number of iterations we've specified. And within that, we have 2 for loops, one for the discriminator and one for the generator. It's very hard to visualize what's going on with a GAN and how it's behaving. TensorBoard, fortunately, is a wonderful tool to get some insights into how the GAN is behaving and what parameters we need to change. Here are the steps to activate TensorBoard. This is a graph visualization that TensorBoard created for our GAN model. Let there be generation. So this is the discriminator error over 10,000 iterations for 2 runs of our GAN model with different parameters. As you can see, the discriminator error is increasing over time. This is the generator error for the same 2 runs. As you can see, the dark red model did fantastically, and its final error rate was 0.5014, which is absolutely fantastic. That particular model had a learning rate of 0.002 for the generator and 0.001 for the discriminator. Here we are visualizing the real data, which is blue, versus the orange data, which is generated for every 1,000 iterations. And you can see it starts off as a single data point of noise and slowly morphs into the shape of a parabola. At iteration 10,000, you can see the real data and the generated data very closely resemble each other. The dreaded live demo. I believe that seeing a GAN in action by a TensorBoard is magical. So let's experience the magic.
We have about 30 seconds left.
So this is our notebook, and I'm going to restart and run all. And soon you will see that the model is iterating, and there's the first iteration. And every 100 iterations, it's going to give me the updated discriminator and generator error. Let's pop over to TensorFlow. And I'm going to refresh it manually because it refreshes every 30 seconds. So you can see the light blue line is the model that we're just running. And
all right, out of time. Do you have a final result?
All right. So that is actually it. And Let's go back to the slides, and we would like to all thank you.
All right. Thank you. Nice job. Very complicated topic, and you handled it very well. I'm impressed.
Yeah.